Today we're going to talk about 2.2, more on functions and their graphs. So this may be a two-part video as I have a lot to cover. So the objectives here will be to identify intervals on which a function increases, decreases, or is constant, use graph to locate relative maxima and minima, test for symmetry, identify even and odd functions and recognize their symmetries, understand and use piecewise functions, and find and simplify a function's difference quotient. So first let's talk about increasing, decreasing, and constant function. A function is increasing if the y values continuously increase as the x values increase. A function is decreasing when the y values continuously decrease as the x values increase. And a function is constant if the y does not change as the x values increase. So let's look at this graph. We're going to state the intervals on which the given function is increasing, decreasing, or constant. And we're going to write our answers in interval notation. Okay. So for increasing, we're going to find the region where the graph goes up from left to right. For decreasing, we're going to look at where the graph goes down from left to right. And then for constant, it'll be a horizontal line. And when we read these graphs, we're going to look at the x values. So on this graph, it peaks here, and that point here is -1, 1, and it bottoms out here, and that point is 1, -1. So let's look at where the graph is increasing. So anything over here would be negative infinity, over here would be positive infinity. So as you can see, this graph is increasing. It's going up and it hits this point, and this point is -1. Like I said, we look at the x values. So it's increasing from negative infinity to -1. Then it looks like it decreases. It goes down till it hits this bottom, and it's going from -1 to 1. Once again, we look at the x values. And then from here, from this bottom, it goes back up. So it looks like it goes from 1 all the way up to positive infinity. Okay, so it's never constant. You don't see a horizontal line on this graph, so it's never constant. So it's increasing on those intervals and decreasing on that other interval. So let's look at another graph. Here, these graphs don't have arrows, so this is where it starts and stops. So this point here is 0, 3. This point here is 1, 1. This is 2, 1. This is 4, 4. And this is 6, 1. Alright, so let's look at where the graph is increasing. And I'll put it all up here. Decreasing and constant. So let's look at this graph from left to right. It looks like from the first point, 0, down to 1, it is decreasing. Look at the x value. So from 0 to 1, it is decreasing. Then it goes over from this point to this point, and then you have a horizontal line. So that's a constant. So it's constant from 1 to 2. Okay, from this point 2, it goes up, and it looks like it goes up to 4. So it's increasing. So from 2 to 4, it increases, and then from this 4, it goes down. It's decreasing. So it decreases from 4 to 6. Notice I'm only using the x values. Okay. Let's look at this next one. I'll go ahead and put the points on here again. This here is -5, 6. This point here is -1, 1. Then this point here is 3, 6. And there's no this arrow, so there's no point. So this is negative infinity. This is positive infinity. So let's see where the graph is increasing. decreasing, and it's constant. So if we look here, we have a I'm sorry, I got my negatives mixed up. This is negative infinity, this is positive infinity. Sorry about that. Alright, so if we look here, there's a horizontal line, and it looks like it's coming from negative infinity to negative 5. So this is constant, negative infinity to negative 5. Once we get to negative 5, the line drops, and it drops down to negative 1, so it's decreasing. So from negative 5 to negative 1 is a decrease. Once we get to that point, it looks like it swoops back up, and it goes to 3. So it's increasing, negative 1 to 3. And then 3, we're going down, it's decreasing, and it looks like it's going from 3 all the way out to positive infinity. Alright, so now we're going to talk about using the graphs to locate relative, maximum, and minimum. A relative maximum point is a point where the function changes directions from increasing to decreasing, making that point a peak. Then you have a relative minimum, and that's the point where the function changes directions from decreasing to increasing, making that point a bottom. The relative maximum and minimum deals with the location on the x-axis. The relative maximum minimum deals with the height on the y-axis. So make note of those different terms, maximum and minimum, and maxima and minimum. So if we look at this graph here, we're going to find the relative maximum and the relative maxima, as well as the relative minimum and the relative minima. So as you can see, we have a peak here. This point is 112. We have a bottom here. This point is 4, negative 15. So let's look at the relative maximum. Okay, remember I said the relative maximum deals with the location on the x-axis. So we're going to look at the x value for the relative maximum. And this x is equal to 1. The relative maxima is the height of this point, and that's along the y. So your relative maximum will be 12. Now if we look at the relative minimum, it's the location. This is the bottom. So this location along the x is 4. And then the location on the y will be negative 15. Alright, next we're going to talk about the test for symmetry. The graph of an equation is symmetric with respect to the x-axis if replacement of y with negative y results in an equivalent equation. It's symmetric about the y-axis if you replace the x with negative x and you get an equivalent equation. And it's symmetric about the origin if you replace x with negative x and y with negative y and you get an equivalent equation. Alright, so let's look at an example, and these can get a little bit long. That's why I had to break this up into 2 videos, but let's see if we can get through a couple. So in this first one, we're going to determine whether or not this equation is symmetric about the y-axis, the x-axis, or the origin. You can also have more than one of these. So let's look at symmetry about the x-axis. To see if it's symmetric about the x-axis, you're going to set y equal to negative y. Okay, so I'm going to change this y to negative y, and then I'm going to go ahead and solve for y. I'm going to get y by itself. So to do that, I'll divide everything by negative 1. I end up with y is equal to negative 5x squared minus 4. So in order for this to be symmetric about the x-axis, your result has to equal your original problem, and it does not. So this is not equal to the original problem of 5x squared plus 4. So it's not symmetric about the x-axis. Okay. So now let's look at symmetry about the y-axis. What you're going to do is you're going to set x equal to negative x. Okay. Then we're going to go ahead and calculate this out. Negative x times negative x will give you a positive x. So you get 5x squared plus 4, which is what our original equation is. That's what we started off with. So this is equal to 5x squared plus 4. So yes, this is symmetric about the y-axis. Okay, so now we're going to see if it's symmetric about the origin. And to check that, we're going to set x equal to negative x and y equal to negative y. So you get negative y is equal to 5 times negative x squared plus 4. This leaves me with negative y is equal to positive 5x squared plus 4. Divide everything by negative 1. We get y is equal to negative 5x squared minus 4. As you can see, this is not equal to our original problem of 5x squared plus 4. So no, it's not symmetric about the origin. So the only thing it's symmetric about is the y-axis. If I were to draw this picture, if I were to draw this graph, it'll look like this. Well, you know what? No, it won't. Hold on, let me erase this. Okay, so this graph would look like, it goes down some, so it should be something like this. There we go. So I'm not good at drawing. So if you were to fold this graph along the y-axis, these two red lines would be equal. They will connect. They will overlap each other. So if you fold it along the y, this is the y-axis. It's symmetric. Okay. All right, let's see if we can do another one in there. The next one says determine whether or not the graph is symmetric about the x, the y, or the origin or more. So we got 3y to the fourth minus 2. Let's check the symmetry about the x-axis. We're going to set y equal to negative y. We get x is equal to 3 times negative y to the fourth minus 2. Okay, so if you were to multiply out these y's, you end up with 3y to the fourth minus 2. Okay, so that's equal to our original problem of x is equal to 3y to the fourth minus 2. So yes, this is symmetric about the y-axis. I'm sorry, the x-axis, not the y-axis. This is symmetric about the x-axis. So now let's check for symmetry about the y-axis. And to do that, we're going to set x equal to negative x. We get negative x is equal to 3y to the fourth minus 2. To get x by itself, we divide everything by 1. I get negative 3y to the fourth plus 2. Okay, this is not equal to our original problem of 3y to the fourth minus 2. So no, it is not symmetric about the y-axis. So now let's see if it's symmetric about the origin. We're going to set x equal to negative x and y equal to negative y. So we get negative x is equal to 3 negative y to the fourth minus 2. We get 3y to the fourth minus 2 with this negative x in front. Divide everything by negative 1. We get x is equal to negative 3y to the fourth plus 2. This is not equivalent to our original problem of x is equal to 3y to the fourth minus 2. So no, it's not symmetric about the origin. So if I were to draw this picture, the graph will look something like this. Okay, so if you were to fold it along the x-axis, those two red lines will overlap. So that's why it's symmetric about the x-axis. All right, let's look at another one. We got x squared plus y squared is equal to 16. So first let's check symmetry about the x-axis. We're going to set y equal to negative y. I get x squared plus negative y squared is equal to 16. Negative y squared is just negative y times negative y, which is just y squared. So this is equivalent to our original problem of x squared plus y squared is equal to 16. So yes, this is symmetric about the x-axis. Okay, so let's do symmetry about the y-axis. We're going to set x equal to negative x. So we get negative x squared plus y squared is equal to 16. Negative x squared is just negative x times negative x, which is just x squared. Then we got y plus y squared is equal to 16. This is equal to our original problem. So yes, this is symmetric about the y-axis. Now let's see if it's symmetric about the origin. We're going to set x equal to negative x and y equal to negative y. So we get negative x squared plus negative y squared is equal to 16. We know that's x squared plus y squared equal to 16, which is equivalent to our original equation. So yes, this is symmetric about the origin. Okay, so if I were to draw this picture, this equation is actually a circle. So if you were to draw this, I'm not good at drawing, so imagine that this is a perfect circle. I just can't draw, that's all. So if you were to fold this along the y-axis, the graph will overlap. If you were to fold it along the y-axis, once again the circle will meet up, it will overlap. When it says symmetric about the origin, that means you turn it upside down. And if it looks the same as it is right side up, then that means symmetric about the origin. Another example of symmetry about the origin is a graph like this. So if you had this and this. Now when you draw it on your paper, I'm not able to flip this, I don't think. I don't know if I can flip this document. Anyway, if you turn it upside down, the graph will look the same as it would right side up. So that's what it means about symmetry about the origin. Okay, so this is part 1 of the lecture. I'll do part 2 in my next video.